Unfortunately, the slides that I've written on 2 weeks ago, they disappeared in somewhere in the nirvana. I couldn't find them anymore, so I have to restart a little bit with this kernel PCA, because that's where we stopped. But I will go through it rather quickly, and whenever you have questions, as usual, write it in the chat, and we will have a break in like 25 minutes and see what questions there are. Right? Okay, good. So hope you can all see the screen. So summary, I call it summary because we started with it already last time. If we look at principal component analysis, we had, I talked about the kernel trick, and the kernel trick allows to extend machine learning algorithms to their kernel version. If we, and this is what we said, if we replace somehow this inner product X transpose Y with a kernel function kappa XY, right? And in order to do that, everything that this algorithm uses should be expressed by inner products. And then we have seen last time that there is this abstract version in this abstract Hilbert space, where we can think about a linear version or a usual version of our machine learning algorithm in this Hilbert space. I would not go so much into the detail here. I would just like to convince you that we can formulate principal component analysis by just using inner products. And we have to recall the standard PCA, where we, of course, don't use only inner products, but where we directly go into the data. You can think about what this standard PCA was. You can have me thinking. So there was this input. Input were the raw data, x1 to xn. Was our data in RP. Then next step was centering the data, right? So we centered the data and replaced here this xi with xi minus mu, or mu hat, and mu hat was nothing else than just the average of all the data, 1 over n, and I write it here with this data matrix times 1. Right, so this is the way I like to write it. Right, so this and 1 here, whoops, 1 is this vector only consisting of ones. Okay. So that means that we have our centered data matrix x bar, which is nothing else than the data matrix X. And then we subtract this mu hat, 1 over n times x times 1. And we subtract it for every column. So there is this 1 transpose here, right? Okay, and we can write that in a more compact form. So this is x times h, and h is this matrix identity minus 1 over n, 1 transpose. Right, and it is the identity matrix. Okay, so once we have this centered data matrix, we computed the SVD of x bar. So that was the crucial step. And we said that this here we named it U sigma V transpose. And then we have the principal components of our data X is given by S, the reduced variable was here UK times X bar. You know, UK were the first K columns of the matrix U. And we've seen that this is nothing else than the sigma K times VK transpose. So these were the principal components of the data. And for a new data point, for a new data point, call it Y in RP, we had this S new was the UK transpose times sorry. Yes. So there is the UK transpose missing here, right? Ryan? Yeah. So there was the transpose. So it's UK transpose times, and then we have our Y minus the mu hat. And then we have the K principal component of a new data point. So that was the standard PCA in a nutshell, right? And and if I look at this, you know, algorithm, I say, okay, so where the heck are inner products here, and how can I use them? So it's not obvious at this point, but it's possible, and this is what we would like to do now. So in the next step, we assume that we only have the non-centered gram matrix K, right, of the data available. So this is all we can use, right? And this means that, so that means here these inner products Xi transpose Xj, right? And the relation to the centered gram matrix is because we want to deal with the centered data, and the relation to the centered gram matrix is so the gram matrix here K that we have is X transpose times X with the non-centered data, and the relation to the centered gram matrix is if we have here K tilde being the centered gram matrix, meaning this is X bar transpose times X bar, we see that we have here this X bar is X times H. So H is a symmetric matrix. So this is H times, okay, let's do it slowly. This is X times H transpose times X times H, right? And H is a symmetric matrix. So this is H times X transpose X times H, and this is H times K times H. So that's cool because we can somehow compute the centered gram matrix, or the gram matrix that would arise from centered data, without explicitly centering the data, but by just modifying this gram matrix K that we have. So that's the good thing. So this is the relation to the centered gram matrix. Now, if let's go back and look at this algorithm. So what we have here is the singular value decomposition here plays a crucial role in our principal components. And we have the U and the sigma and the V transpose of the raw data X. But we do not have access to this raw data X. We only have access to these inner products. That's what we want to do. And that means what parts of the singular value decomposition can we somehow extract from only the centered gram matrix? And and the good news is that if we only have this X bar transpose X bar, right, we can still extract the right singular vectors of our X bar. namely the components that we use or the information that we have in this V transpose here, this part. And this is because of the relation of the singular value decomposition and the eigenvalue decomposition of matrices, and so we can have access to this V, and that is already a good first step. So computing the principal components using only the centered gram matrix is what we want to do next. And the good news is that we can get this VK transpose from an eigenvalue decomposition of the centered gram matrix, right? And this is because you know, I mean, if we have X bar is U times sigma times V transpose, if this is the SVD here of X bar, then it follows that X bar transpose X bar is V times sigma transpose times sigma, but this is this diagonal matrix, so this is sigma 1 squared to sigma n squared depending on the size here, times V transpose, that this here is an eigenvalue decomposition of this K tilde, right, which is nothing else than K bar X bar transpose X bar, right?
Yeah.
And this is, so, you know, this is this direction, and in the other direction we have that if V times lambda times V transpose is here K tilde, if this is an eigenvalue decomposition of K tilde, then V, this orthogonal matrix, are the right singular values, are right singular values of X bar. Okay.
I have a question here, Martin. Can you please clarify a bit, what do you mean by right singular values?
Well, the right singular values are the not values, vector, the right singular vectors. Sorry.
Yeah.
I'm sorry. The right singular vectors is just, so if you in general have the singular value decomposition of some matrix A, which is U times sigma times V transpose, U, so the vectors in U are called the left singular vectors, and the vectors in V are called the right singular vectors. So this is the naming and the definition here. Okay. So and that's cool, because that means that once, I mean, if someone gives us this K tilde, we can compute the singular value, the eigenvalue decomposition of this K tilde, and this allows us to compute the V, and it's exactly the V that we need for our X bar. So that's cool. So that means that we have access to this V transpose here. Okay. So that's cool. So we can have the first K singular vectors, and and then compute it. Good. Yes, so there is something there is something that one needs somehow to understand in relation of the relation of the singular value decomposition of a matrix A and the eigenvalue decomposition in general of a matrix A transpose A, right? So a singular value decomposition of A and the eigenvalue decomposition of A transpose A, what is the relation to that? This is what you need to understand here. Yeah. Good. Then, are there any questions to that point here already?
Not here.
Okay.
But I just was wondering if we like have some comment on the relation between singular values and eigenvalues also here.
Yeah. So that's completely true. Okay. So I think we should look at this point here. Let me. Let me erase that for a moment and rewrite it again. Okay, so we have here this, so we are looking at the singular value decomposition of A, which is some U sigma V transpose. And on the other hand, we are looking at this A transpose A. And we will look at this at the eigenvalue decomposition here. Okay. So the first fact is that this matrix A transpose A is a positive symmetric semi-definite matrix by construction. That means that the eigenvalues are non-negative. And that also means that it has an eigenvector decomposition, or that it has eigenvectors that are orthogonal to each other. So this is, this is just, this is because of the positive semi-definiteness of the matrix that we want to decompose. Okay, so that means we can write this eigenvalue decomposition as something like V transpose, or something like V times V transpose, and the eigenvalues here, lambda I, are greater or equal to 0. Okay, and V is and V is orthogonal. And orthogonal means that the transpose is the same than the inverse. But this is really only true because A transpose A is positive semi-definite. Okay, good. Now the relation between the sigma and the lambda I is that the sigma i's here, or that the lambda i's here are the square roots of the sigma i's. So sigma I square is lambda I. Right, this is the relation. And you can, yeah. Is that clear enough? I mean, I could go much more into the details, but I think for that point here, it's
totally clear.
Okay.
For me.
Okay, good. So so that's the cool thing, right? Because this, and that's crucial, because this x bar, this x tilde is here positive semi-definite. Okay, good. Then so that's fine, right? Because that means that well, why not? So that means we can compute the principal component of our data x very easy, because it's this, this vk transpose times, and then we have this lambda k, which only take the first k entries of the lambda, right? And the square root of it, right? Because this are the PCs of our data. Right, this is S. And we can compute everything just by using the Gram matrix. Right, this is this relation here. Okay, so that's why you need it. Right, and lambda k to 1/2 means we just take the it's a diagonal matrix and we just take the square root of the lambdas here. Okay, good. But what if a new data point is coming in? And then it's more tricky, because if a new data point is coming in, we said that, well, we need the UK transpose. We need this left singular vectors of the singularity decomposition of our centered data matrix X bar, and this is not available for us. And we cannot. I mean, what we would like to have is we would like to have this, UK transpose times y minus mu hat, right? But the UK transpose is not nothing we have at hand if we only want to use inner products. Okay, but this is not so much of a problem, because what we can do is, and I'm always thinking about, so it's a kind of how I remind that, or how I remember that is, right, we have the X bar is the U times sigma times V transpose. If I want to come with this, oops, so this U is somehow on the left side here. So what I do is I just start the computation and say, okay, so what happens if I take this X bar transpose and multiply that with this my minus mu hat? Right, this is something I could compute, right? And this is something where we have the V and the sigma transpose and the U transpose times y minus mu hat. Okay, so the U transpose meets the Y here already. And if we take this equation and if we multiply this equation from the left with our VK transpose, the VK is something that we have already computed, you remember? That's something we can get. And if we compute, so the VK transpose from the left leads us to this equation. Say, okay, so this is VK transpose times X bar transpose times y minus mu hat. And the VK transpose meets the V. Remember the VK, if this is V, then this here is the VK, right? The first K columns. So if the VK transpose meets the V, the first part here of this matrix is the identity because it's orthogonal, and the last part is 0 due to the orthogonality, right? And what remains is the sigma transpose times the U transpose times y minus mu hat, right? And if we further look into what's happening here, this matrix here is, ik and 0, so there are lots of zeros here, and the first part, this, if we multiply this here, that leads us to sigma k 0 times U transpose times y minus mu tilde, right? And that only, somehow digests the first k columns of the UK transpose here. So what is there indeed is just the sigma k times the UK transpose times y minus mu tilde. And that's pretty cool, because what we see here is that if we now take this equation and multiply this equation on both sides by the sigma k to the minus 1, we see that sigma k to the minus 1 times vk transpose times x bar times y minus mu hat is the same than UK transpose times y times y minus mu hat. And this is cool, right? Because that means that we have all this data on the left-hand side available. We have our sigma k, our sigma k's, because they were just the square roots of the lambdas that came from the eigenvalue decomposition of the centered Gram matrix. We have the vk transpose, which are just the first k eigenvectors of the Gram matrix, the centered Gram matrix. We have, with x transpose y, a set of inner products, right? Because although we don't know this x transpose, we have here inner products of the first column of x with y, of the second column of x with y, and so on and so forth. So let's have a closer look into this x bar transpose y minus mu hat and see whether we can use that here with this paradigm that we only want to use inner products. Right, because so this is what remains. We have x transpose y minus mu hat, x bar transpose y minus mu hat, right? This is, well, x bar was xh transpose, right? Times y minus mu hat. And mu hat was you remember? Mu hat, that was just the centered data matrix 1 over n times x times 1, right? And that is h was symmetric, so this is h times x transpose times y. Oh no, I am not available. H times x transpose times y minus 1 over n h times x transpose x times 1. And that's cool. This is, this is h times, and here, as I said, we have this x1 transpose y up to xn transpose y here, minus, and this here is 1 over n times h times the non-centered Gram matrix K, which was the input that we have available, times this vector 1 here. Right? So this K can be computed by only using inner products, and we don't have to center anything else. We have this H, we have this H here, we have the gram matrix K, and we have the sigma K to the -1, we have the VK transpose here. This here is doable by just using inner products, and so that means we can use the kernel trick now to replace everything that is with inner products with the kernel, and this is the birth of kernel principal component analysis, if you want. So how does that, if we summarize it, how does it look like? Well, if we summarize it, we have we have just to replace the inner product with kernels. So instead of having these xi transpose xj as inputs, we have a kernel function k, and we compute the kernel evaluated for all the input data xi xj. This gives us this matrix k. Then we can compute the gram matrix that originates for the standard data. Here by k tilde is hkh, as we just did. And in the next step, we compute the singular values, we compute the eigenvalue decomposition of this k tilde here. Eigenvalue decomposition of this k tilde, which is the v lambda v transpose. Now remember, the definition of a kernel function ensures that the matrix k tilde that we get here is always positive semi-definite, right? It ensures that this matrix k is positive semi-definite, and if k is positive semi-definite by the positive semi-definiteness of the h, also this hkh is also positive semi-definite, and that ensures us that our computer can always compute the square roots of the diagonal entries of the lambda. Okay. So if you get an error here, if you do the eigenvalue decomposition of the k tilde, and you have negative eigenvalues, then that means that someone gave you a bad kernel. Okay, so then, and due to the definition of the kernel functions, as I said, this matrix is positive semi-definite, and then also we have this relation here that we also discussed and said that we can think about this diagonal as squares here. The reduced matrices sigma k and vk are as usual, and then we have the reduced training data then given by this S is sigma k times vk transpose. Yes, that was the first step, right? And for a new data point coming in, we have to do what we did beforehand. We have our new data point. This was sigma k to the -1 times vk transpose times this vector k nu centered, and the k nu centered is, as we computed here, just h times k nu -1 over nk, and you know, this is just the summary of what we wrote by just replacing here this inner product with this kernel function k is x1y up to xny. All right. Okay, so now, I mean, what you have to do now is take some real-world example and play around and compare the standard principal components with the kernel principal components. Get a feeling for how, you know, I mean, how large your data set might be, because the problem of the kernel PCA is that the matrix that you deal with is of order squared by the number of training data that you have. Right? The gram matrix is an n squared matrix, and n is the number of data. So of course this is somehow limited. And what you do in practice is you reduce the data very often with a usual linear PCA, where you reduce the data from, I don't know, perhaps 10,000, dimension 10,000 to 500 or so, or 200 or 300. And with that, you start doing a kernel PCA afterwards in order to deal with that. Right, so play around and look at the analysis and see whether the reduced data or these kernel principal components are really a benefit to your analysis. Okay, but this is something you do in the tutorials, probably.
Yeah.
Very good. So then let's have a short break. Let's collect some questions. So if you have some questions, I think I would give you like 5 minutes or so, we restart at 10:27, and I'm looking forward to your questions then. Okay, see you again at 10:27.
Okay.
Mute tilde in your head. Oh, okay, I'm sorry.
Oh.
Okay, so this is that I mean mu hat.
Okay. Okay, thank you.
So the mu tilde is the same in the mu hat.
Okay, thanks.
If I write that down. If you look into the lecture notes, it should be more concise, the notation. I do hope. Okay, good. So if this is all that we have for kernel principal components, then I would jump to the next part of the lecture, which is the interesting support vector machine, right? And or are there other questions, Ryan? No.
No.
Okay. Beibehalten. Okay. So that was this thing here. Wow. I like it if the technique is working. That's awesome. Support vector machines. Okay, support vector machines. I mean, they are they have been very famous, and they are still very, very useful. And although they are somehow getting out of scope in the research area, from a practical point of view, they are still very very important, because they provide very easy. It's a very easy and easy to implement and very powerful method for binary classification tasks, or for classification tasks. And so this is why, and it gives you another perspective on how machine learning techniques can work. And so I thought that it's quite important and useful for us to put that into this lecture. So this is why they are here. Okay, good. So what's the motivation behind these support vector machines? So the setting that we have is, well, it's a supervised binary classification problem. We have our input, X. Oh no, I don't like red here. Prefer blue. Oops. Where we have our input X. Random variable RP, and our output Y is binary, and it takes here -1 and 1 as the two possible outputs, right? And we already had that setting when we were looking at the logistic regression problem, and it's somehow related to the logistic regression problem, and I would like to use that for the introduction here. So if we consider the 0-1 loss function, do you remember that? So the 0-1 loss function is a function that measures, so it gives you a penalty if what your function f predicts and what the true output is, if the signs do not coincide here, the sign of y and the sign of f of x, if they do not coincide, it penalizes here your loss function with a 1. And if both sides coincide, you have a 0 here. Right? This was the famous 0, 1 loss function. And if you consider the function f here, hold on, if you consider the function f yeah, okay, so that was this loss function, exactly. And if you consider here the decision function to be an affine function, that means you know, that means the f of x that we have is given by w transpose times x plus b. Then the data, and so if we consider this as our decision function, and if we consider the data to be linearly separable, linearly separable means that we have here the, you know, the y is -1 party, and on the other side we have the y is +1, and linearly separable means that we can somehow fit a hyperplane here into our sets of data points that separates the ones here from the other ones. And if this is the case, and if we consider the 0, 1 loss function, then we can find affine functions or affine decision functions f of x that reduces our loss to 0, right? So that exists because it separates the data. So if this f of x is given here in that way, we can always map the outcome y and the point x is having the same sign. Okay, and not only this this linear function separates it, but there might also be, I don't know, perhaps let's draw it in another color, perhaps orange. You might also have, I don't know, this linear function. So you see that there is some room to somehow arrange this hyperplane that separates this function, and we want to have a closer look at that. And support vector machine, if you want, is a way of finding an affine function that best separates the data. Okay, so the setting that we have is, for the moment, we assume that the data is linearly separable. Perhaps if I draw it, yeah. If I draw it in only 2 dimensions and not in 3 dimensions, it might be a little bit clearer, right? So actually, it's not so difficult actually. So I mean, here is one class, here is the other class. We have here the function, linear function w transpose x plus b is 0, and if this is the decision function, then we have a loss of 0 here, and if this here is the decision function, we also have a loss of 0. And there are many, you know, many affine functions that separate that data. And the idea of support vector machine is to find an affine function that best separates the data. And and it's a very geometric, intuitive way of looking at that. And so we have to go and look a little and see what the geometry is. So perhaps I'm spoiling already what the idea is. Among all these possible hyperplanes that separate the data, there is one that allows, if I think about thickening these hyperplanes, so I blew them up like a matrix, Luftmatratze, air matrix, right? I blow it up and see how thick it can get. And thick means how thick can it get before it touches one of the data points that we have. I think this is the right intuition. So there is, so this allows for a thickness of, I don't know, this one, and the other allows for a smaller thickness because it's only, if I blew it up, it's only here and so on. And so what we want to do is we want to find a hyperplane that allows for the largest thickness of the data. And that's the idea. Yeah, so, and this is why we have to look a little bit into geometry to in order to be able to formulate what we want in a mathematical way. Right. I don't like that. Yeah, it's as it is. Good. So some geometry, right? Perhaps that should be familiar to you from your, I don't know, high school perhaps, or later on. And sorry. Yeah, so we have to define the mathematical objects that we are dealing with now. And the definition here for an affine hyperplane is, I call it H, W, and B, because it depends on a set of parameters. We can describe this affine hyperplane as all x in Rp, such that there is an affine function such that W transpose times X. Such that W transpose times X, I have here minus B, it doesn't matter, minus B is equal to 0. So this defines affine hyperplanes in Rp. Like this ones. H, W, and B. The vector and W is some vector in Rp. And the vector W is perpendicular to that hyperplane. W is Yeah, normal or perpendicular to this hyperplane H. This is one important thing, and that means two hyperplanes are parallel if the describing vectors W are multiple of each other. Okay, so that means that HW B and HW tilde B tilde are parallel if and only if W is lambda times W tilde and lambda is a real number not equal to 0. Okay. So that's what we need. And what else do we need? Well, we need to have an understanding of the distance of some point x to this hyperplane here. So the distance of x to h, how can we compute it? And we we distinguish between a distance from one side and distance from the other side. So we define assigned distance to the affine hyperplane, and this distance is given in the following formula. So it's the signed distance to a hyperplane. So distance from x to a hyperplane that is given with these parameters w and b is given by w transpose x minus b divided by the norm of w. Okay, so here this is the picture again. And so here, this here is distance of x h. And it's positive for x lying on one side of the half plane, and it's negative for points lying on the other side of the half plane. And this is important for us if we want to distinguish between positive on one side and negative on the other side, because, you know, think of our loss function. And so it makes sense. I omit the proof. So if you, the proof is in the lecture notes. If you want to have a look at it, you can try to follow it. But I think we would save the time here and would not prove it. Just give you the result here. Okay, because so if we think about blowing up such a hyperplane, so that was the image that we had in mind. So we have here this hyperplane H, and we have another hyperplane that is parallel to it here, and here. And we define here this, given this H, we define the H plus by terms of H plus is given by all x in R P such that W transpose X minus B is equal to 1. And we define H minus to be the hyperplane, we say X in RP, such that W transpose X minus B is equal to -1. So that we have like thickened a little bit the original plane H. And the margin of H is actually the the margin is defined as all points that lie here in this sandwich. So everything that lies between this H plus and this H minus, right? Mathematically spoken, we say that the margin of H is the convex hull of H plus and H minus. So all points that lie in between. So this is the margin, and the margin has some thickness. The thickness of this margin comes, of course, with our signed distance to the hyperplane, and the thickness of the margin is, so a point that lies here at this H plus, right, so if X is in distance from X to H, if X is in H plus, well, X is in H plus, so the distance here is given here. Here is the formula. It's W transpose X minus B divided by the norm of W. So the distance is here X W transpose minus B times the norm of W, and this is exactly 1 divided by the norm of W, because it's just a definition of so let me try to write that more clearly. X transpose W minus B divided by the norm of W, and X transpose W minus B is here by definition given by 1. So this is 1 over the norm of W, and that means that the thickness is given by 2 over the norm of W, right? Because we have it 2 times. 1 coming from H plus to H and then from H minus to H. So this is the thickness, and the optimization problem that we ultimately have is okay, so we want to maximize the thickness. So that's one thing, but of course we want to have a constraint, namely that that all points that lie here on one side of the hyperplane do not interfere with the margin. That's the thing. So all positive points, or all points where we have x is, the label is +1, have to lie on this side of h plus, and all the negative ones have to lie on the other side of this h minus. And these are constraints that we have to maximize, that we have to make precise. And no data point inside the margin means that, so let x1, y1 up to xn, yn be our training data. These constraints means that W transpose times xi minus b has to be larger or equal to 1 if yi is +1. And we have W transpose times xi minus b has to be lower or equal to -1 if yi is -1. Right, these are the constraints here. And that is precisely the same than saying we have yi times W transpose times xi minus b is greater or equal to 1 for all training data. It's 1 to n. So these are the constraints, and that leads us to the optimization problem. Finding the hyperplane that allows for the largest margin yields 2. We want to maximize this guy here, right? The thickness of the margin, subject to satisfying the constraints that no point lies within a margin. This is yi times W transpose xi minus b is greater or equal to 1 for all I is 1 to n. Okay, this is one thing, but instead of I mean, it's hard for optimization problems to look at this problem because you have here the W here in the denominator. It's easier, and equivalently the same thing if you, instead of maximizing 2 over W, you minimize 1 over the function. So you minimize the norm of this, and right, you minimize 1 over this cost function, and not only that, you also take a square of it. So it's easier for optimization purposes to look at the problem, to the equivalent problem. Equivalently, we want to minimize norm of W squared, and you often use 1/2 there, because if you take the gradient, then this cancels, but it's the same and it's equivalent with the same constraints here, subject to yi W transpose xi minus b, well, -1 is greater or equal to 0 for all I is 1 to n. So this this is our optimization problem, and It's actually a nice problem. This is convex. And right, I mean, we have convex constraints here. This is convex and can be solved. Rather easily with a computer, right? And so this will output us a W and it will output us a B. And with this B, we will have a decision function that allows for the largest margin and is in that sense optimal to decide if when a new data point is coming in, whether it lies on one side or the other side, or which class it belongs to. Yes. So that was the first step of looking into the support vector machines, and then we will go further. But I would like to have a short break here for a moment and see whether there are some questions so far. Right, let's give us like, why not 3 minutes or 4 minutes up to 11:03 and see whether there are some questions. If you don't want to write it down in the chat, you can directly, use the mic and ask.
Hi, I have a question.
Go ahead.
So if I have understood it correctly, so we're optimizing over W and B,
Yes.
right?
Yes.
But only W has an effect on our objective value.
Yes.
How do we choose B then?
Well, B will be chosen by our optimizer because B has an effect in the constraints, and so it indirectly has an effect on the W. Right here,
Okay.
Here is the B.
Okay. I'm just confused how I would solve it if I would try to solve it analytically. How do I incorporate B? But I maybe might have to think about it. Just okay. Yeah. Thank you.
Yeah. I mean, from an intuition, it's if you choose a better B, it may allow for a smaller W. Right.
Okay.
So it depends, and it has some influence on it.
Okay.
Right? And the way you solve it, we will go a little bit deeper into how to solve that in the next step. So it might also become clearer during the lecture in the next coming minutes and hours.
Okay, thank you.
Yeah, the B will be actually substituted there by available data. So
Ryan, you can stop the recording if you want. I still want to wait 3 minutes because perhaps there are other questions.
okay.
So it seems that there are no further questions. That's good so far. Now, if you think about the former times when people were not so lazy than today and used the computer for solving any problem, for example, in high school, you had a minimization problem, and what you did is you built a derivative, you set it to 0, you try to analytically find a solution. You remember? The more you can do that, the easier it will be for a computer later to work with that, right? Ideally, you don't need a computer at all. And this is actually the motivation why we want to dig a little bit deeper into these kind of problems, right? Because although it's a kind of, it's a convex optimization problem, we may have further insights into the problem if we look at it deeper, right? And the parallel association is like what you did in high school by building derivatives, looking at where is it zero and what explicit formulas you can have for an optimum. Okay, so that's the thing. That's one thing. And the other motivation is that once we have done that, we will be able to formulate the whole algorithm just using inner products. And then you can imagine where the story goes. Okay, so these are the two motivations why we look a little bit further now into that problem. And to see where the problem is, I would like to get one step more abstract and look at an abstract theory, because there's the theory of convex optimization that there are lots of books on that, and lots of people have thought about these things. So I want to get one step more abstract and look with you on this general problem on convex optimization, where we have a minimization problem. So we want to minimize some function, some real value function f, and we have two kinds of constraints. We have equality constraints. So functions ci for which we say ci of z is 0 for all e that are here equality constraints. So this is for equality constraints. And we have the function cj of z where we have this inequality constraints. Inequality constraints. And many, as I said, many books deal with that problem on convex optimization. And if you want to go further into the research area also of machine learning, I think it's hardly possible to do that without having a closer look into these books. Okay, but this is not a convex optimization lecture, so we will strive it a little bit. I hope, well, I don't know how much experience you have with that convex optimization, but I would like to give you a kind of picture that helps me, and if it helps me, it may perhaps also help you. And the picture is the following. So assume that you have a function, right here you are in Rn, and you have a function f from Rn to R. And of course, I can only draw in 2 dimensions, but what I would like to draw here is something like, these sublevel sets. Right, these are the curves where we have f of z is constant. Right? Right. I'm just drawing 2 because I don't want to. But I mean, so these are the sublevel sets, and on the other side now, what you have is you have another function c, call it c, function c also from Rn to R, and here you have sublevel set of that function c, where we say, so this are all c of z is equal to 0. This is the curve here. Okay. And the optimization problem that you want to solve, or the constraint optimization problem that you want to solve, is we want to minimize here this function f of z, but you have these constraints subject to c of z is equal to 0. right? So actually, you can only walk here on that curve. I mean, here it's a curve. Normally, it's in high dimensions. It's a not a hyperplane, but it's a kind of manifold, at least locally. And then you walk around here that curve, and you want to see, okay, so where? And you're measuring the function f of z as you walk around here and say, okay, so when is this function minimal? Okay, and I think this picture makes it intuitively clear that the point where that happens is the point where these sublevels here are tangent somehow to that curve, right? So it somehow, there is somehow a sublevel set that touches this curve, and this is where, you know, if f is a temperature, this is where the temperature is lowest on that curve. Okay, and that means, and what does that mean? That means that if I have this point x tilde here, then this is this x tilde, it says that, I mean, how can we formulate that mathematically? That means that the gradient of that function f of z and the gradient of the function, the gradient of the function f of z and the gradient of the function, here, c of z, should name it z and not x, sorry, z tilde. Right, that for an optimal z tilde, we have that the gradient of f of z tilde points in the same direction or something than lambda times the gradient of c of z tilde. Right. This is something that I at least can imagine very well. Right? And this motivates us to look at what is called the Lagrangian function. And the Lagrangian function is, the Lagrangian function of z is this f of z plus lambda times c of z, and if we have more of these guys, we sum it up over the ci. Okay, and we see that for an optimal value, the gradient of this Lagrangian function is 0. Right, and yeah, so that helps me, and this is somehow the picture, the picture associated to that formula. So this is the Lagrange function. We have said we have the lambda. The lambda here is a vector consisting of as many components as we have constraints. We summarize the equality and the inequality constraints here together, and we have here this lambda is here of z. And this is Lagrange function for our problem, right? And yeah, so the theorem, I mean so the theorem that we will use and where we will hook on next week again is the so-called Karsh-Kuhn-Tucker conditions. So the Karsh-Kuhn-Tucker conditions say that if we have an optimal solution of our optimization problem, Z star, then under certain conditions on the constraint functions, everything has to be mathematically precise. You could construct other things, but they are very general conditions. Then there exists Lagrange multiplier lambda star. So there exists a particular lambdas such that the gradient of this Z star lambda is 0. So this was the picture that I showed you, such that the constraints are satisfied. That's good. Then, interestingly enough, that the lambda I star are always greater or equal for all inequality constraints. And the last point is probably the one that needs some, that is most surprising. That says that the lambda I star c times x star is 0. So that either, so translated, that means either lambda I star is 0. That means constraint is irrelevant, right? Or the Ci Z star is 0. That means that the constraint is actually an equality constraint. Right? So this is the let's say most interesting, or one of the most interesting findings here in this Karsh-Kuhn-Tucker conditions. So that if you have these inequality constraints, then the optimal value is always like found at the boundary of that regions. Yes, so that's where we hook on next time, and then we try to see how these particular conditions boil down to the problem that we have, and that we find some new insights into the support vector machine problem if we use the Karsh-Kuhn-Tucker conditions. Thanks, and see you again next week. Bye-bye.
Goodbye.